Reality is analog, a wave.
Reality is digital, 1 and 0, on and off.
A vibration resonating in the frequency of visible light strikes the eye, entering through the pupil.
An object stored in binary form is called up as a series of points in space, each related to the other.
Muscles in the ciliary body contract or relax to alter the shape of the lens, depending on the distance to the object being viewed.
In a digital environment, solid objects in three-dimensional space are composed of millions of two-dimensional polygons.
After penetrating the lens, light passes through the vitreous humor and falls on the retina, where the miracle of perception occurs.
With Onyx Infinite Reality, the journey from binary code to 3D photorealism begins when these polygons are called up from memory and sent to the visualization pipeline across the power
Retinal
channel 2 board.
photoreceptors, the rods and cones, convert light into electrical pulses
The
the brain
system makes
can
the
process.
calculations necessary to transform the object and map textures and images onto its surface. Then multi-sample anti-aliasing techniques are used to render each frame.
This image travels the optic
These
nerve,
are each stored in the frame buffer.
imprinting an image on the
And
occipital
the image
lobe
is displayed via millions of
the visual
pixels,
cortex
projected in
far
waves,
in the
red,
back of the
green, and
brain.
blue.
And it all happens in less than 16
milliseconds.
Everything always looks right in the real world. Your brain has the capability of processing and integrating all these different pieces together at the same resolution and providing you a complete image of the world. Well, the computer needs to do that the same way.
The customer wants to see high-resolution graphics, he wants to see real-time, and he wants to see complex scenarios.
We're trying to create realistic images, and this technology is one of the most demanding applications running on the Onyx platform and the Reality engines.
We're competing really with real-world sets and trying to add a level of detail that matches the level of detail in the real world.
In putting together an air traffic control simulation, it's a multi-channel, 8 channels minimum for a 360-degree configuration. So you've got a lot of pixels to pump out.
So we have a dual battle here, not only to create realistic images, but present them in real time.
because the world works in real time.
People that now have simulation databases with geotypical terrain where they have textures of green and brown blobs or just a lake will go to 1 meter photographic data, satellite data, aerial photograph data. You can fly anywhere on the Earth, 60 frames per second, and see your house, your street, your dog.
I mean, I've been a graphics professional for 11 years now. I teach it at the university, and the crispness of the image, it was incredible.
We don't have to give up quality for speed. We can have them both with this system.
It has actually blurred the distinction between real-world video and the actual computer-generated imagery.
This system was more wonderful than I had expected.
I saw the Matterhorn, and it looked like something you could actually ski down.
You could even see the little tracks in the snow where skiers had gone.
Nobody else could do this. Nobody.
It's the fastest, has the most resolution, has the most outputs, has the highest image quality. It brings everything that's ever been done and puts it all synthesized into one easy-to-use portable machine.
My customer, the U.S. Air Force, can now have high-fidelity, high-density, 60 hertz databases without the need for racks of computer systems. It provides not only the image generation capabilities, but also the host computer capabilities.
We can draw over 10 million polygons a second, so by far the fastest geometry rates. It has incredible texture mapping capacity, by far exceeding anything that we've done in the past. And in addition, it has very, very high image processing capabilities.
This machine is 32,000 by 32,000. Okay, it's over 1 billion pixels. This is an enormous 4,000 time increase in texture memory size.
And when you're able to update and refresh a screen at 60 times a second or once every 16.6 milliseconds, you're able to provide a illusion to the person that's looking at the screen that what they're seeing is pure solid motion.
I think once you've seen 60 hertz, it's pretty hard to go back.
Slow people lose.
Rather than build a physical mock-up of a system, We'd much rather do this digitally so that things can be changed on the fly and viewed interactively virtually every day of the design process.
This new system is going to make us a lot more competitive in our markets, both special effects and compositing and in virtual sets. We're going to be able to take on a whole lot more of that market using a standard platform that allow our customers to stay on an open system, run lots of applications on it, and get all of the ROI advantages of continually upgrading on that hardware.
We're really going to change the way we image patients. We're not going to look at the world in a static 2D fashion. We're going to look at volumes of patients' anatomy.
We're going to move from the world of being able to do small pilot studies to see how things might turn out, to actually looking at large numbers of patients and developing techniques that work for them.
Every manufacturer today is looking at is trying to lower the time to market on a product, and that requires the ability to get in and visualize the entire product. And Infinite Reality will give us that ability to do things interactively rather than having to do things offline.
What this is essentially is the equivalent of a CAT scan of the Earth. These data sets are getting very, very big, and so the time it's taken to review the data and come up with a model of the subsurface that's consistent with all the data that's in there is time-consuming. This kind of step forward in the technology is certainly going to shorten that cycle time.
With the configuration Goto will use for planetariums, our main goal is to cover the entire screen of the dome. However, there are some cost issues. But with this system, we are able to offer several different configurations.
What we try to do is to show or give them the ability to look at the whole theater at once. And in order to do that, you have to be able to handle many gigabytes of information. And this system, with its enhanced texture memory capability and texture paging, is going to allow us to move around a whole theater rather than a very small part of that area in real time.
We can now create far more realistic looking sets. And primarily that has to do with the fact that we can render faster, but mainly we can texture much better and faster than we were able to do so before.
If you look at the product that we're building, the F-16 and F-15 unit training device, it's a low-cost, high-fidelity flight simulator. And when I talk about low cost, I mean I'm replacing a previous weapon system trainer that sold for $20 million that had something like 20 racks of computer systems, and I've shrunk it into one platform, one computer that's the size of a refrigerator.
Don't just change the way you work.
Change the way you think.
We're going to be putting tools in the hands of artists that they've never had before, and that'll cause them to do things that we've never seen before. And we'll deliver these solutions to these artists, and a few months later we'll start seeing things on our televisions or on our theater screens that are just amazing.
We're just at the beginning of a whole new era in three-dimensional imaging, and Stanford, I'm sure, will be a big part of it, and so will Silicon Graphics.
It's not that we're just making things 10% faster or changing the price performance by 50%. Those are little baby steps. We're talking about giant steps here.
And it is so powerful that it will truly change the way that people think about doing business.
It'll be as if suddenly they woke up and they were in the 22nd century.